The real world is an ever-expanding, infinite series of random events happening an infinite amount of times. So much so that it would be foolish to think that we could ever possibly predict the outcome of anything that happens, right? Well, maybe or maybe not. But assuming we can, this is where linear probabilistic modeling comes in. When it comes to making a big decision, some of the first questions you may ask yourself is this the right choice? Am I making a smart decision? And what are the odds that this is a success or a failure? We weigh the different factors that go into our decision and come to a conclusion whether to go through with it or to consider our alternatives. In a way, we are modeling linear probabilities, at least in our heads. Let's say that for an event we have a set of inputs and outcomes. We compare each input to their specific outcome and plot it onto a graph called a scatter plot. This allows us to analyze the relationship between the inputs and outcomes, allowing us to predict the probability of a certain outcome based on a trend shown by the regression line. This line is not totally accurate, however, so the outcomes may be above or below the line of regression. This is known as our error. It is important to know this because the real world is not perfectly predictable, but we can still help ourselves by making the best possible decision. To think about it from an engineering point of view, let's say that you're in charge of quality control at a parts manufacturer. You want to find out how many parts the factory can produce in an hour while keeping the amount of defective parts below a certain amount. We model this experiment in increments of 100 and then test until we have made 1,000 parts in 1 hour. In this case, we will either get a probability of 0 or 1, 1 meaning a success and 0 being a failure, depending on if the batch has more than 100 parts come out defective. After collecting our data, we construct the scatter plot. As you can see, the regression line has a negative slope, indicating that the more parts we try to produce in an hour, the more likely we will get over 100 defective parts in the batch. This starts happening 400 parts per hour and then on, with 600 parts per hour being an outlier exception. From here, we can either decide to make 300 parts per hour, or play it safe and go with 200 parts per hour to compromise between safety and speed. Probabilistic modeling has many applications in everyday life and can be very helpful in making decisions when you're not sure what to do. Hopefully you learned something from this video and will continue to think about how you can apply concepts in your engineering career. Thank you for watching.